shells of varying density, and what you see is his shells of varying density intersect with his ones. Now, the only way that can be consistent is if the density of all those shells is the same. In other words, isotropy everywhere implies homogeneity. So I've given you a very simple geometrical argument. If both A sees isotropy and B, what that means is the worst that can happen for A is inhomogeneity with spherical shells, but the same is true for B. But the problem then is his shells intersect with his. So A says the density is the same everywhere on that shell, and B says it's the same everywhere on that shell. Well, that means, if you think about it, that then A can say, but it's also the same on that. Once you know it's the same on these two shells, it extends to everywhere. The density must be constant in space. Okay? And from the space-time viewpoint, what it means is there is a preferred time, T. The pressure depends only on T. The energy density depends only on T. Anything you think of depends only on T. What is allowed is a time variation. Is allowed. And so the standard model of the universe is based on this simple line of argument. We see isotropy. If we are typical, if we're not at the center of the universe, then everybody sees isotropy, and that means the universe is spatially homogeneous and isotropic about every point. So the universe is spatially homogeneous and isotropic about every point, and that is what defines the standard models of cosmology, the Friedmann, Lemaitre, Robertson, Walker models. Okay, the metric tensor. Now, I'm going to shortcut a long bit of argument to say as follows. The metric tensor can then be written, metric is minus dt squared, where this is this preferred time, plus a squared of t, the scale factor as a function of time, into d sigma squared, where that is a 3 space of constant curvature plus 1, 0, or minus 1. We get 3 possible cases. And if you write that out, we get, in the coordinates I like, we get as follows: dr squared plus f squared of r into d theta squared plus sine squared theta d phi squared, where f of r is sine of r if k is plus 1, is r if k is 0, and is hyperbolic sine of r if k is minus 1. And this tells you the metric of the universe. Some people use different coordinates for this 3 space, but this is the one I like to use. And I need to tell you one other thing. The 4-velocity vector is delta A 0, that it is 1, 0, 0, and 0. So this is the metric of the space-time, which I needed to give you to tell you what the space-time is like. And then to have a cosmology, I must tell you where the matter is going. And what this says, we have surfaces in space-time T is constant, and the matter moves orthogonal. It moves orthogonal to these surfaces. T is constant in the space-time. Okay. So, these are the standard models. That's their metric, and that's how they move. Now, A of T is a scale factor. What that means is everything scales with A of T. Everything. So if you look at the universe here at an initial time T1, where you have A of T1, and you have a galaxy there and a galaxy there, G1 and G2. Now, let time evolve, follow the universe through time, and you end up at a second time T2, and that galaxy will have moved there, and that galaxy will have moved there, and that will be the distance D1, and that will be the distance D2, and it follows from here that D1 to D2 scales as A at time T1 to A at times T2. All distances scale like that. So, the Virgo cluster is moving away from us. All the more distant galaxies are moving away. And everything scales with the scale factor A. Now, the question people always ask when they've thought about it a bit is, what about the solar system? Does the size of the Earth scale with A of t? What about the distance of the Earth from the Sun and so on? Well, this is true on cosmological scales. I already mentioned here this averaging scale. This is the averaging scale. So when you use this metric, it does not describe what happens on smaller scales. We need to do something more complicated for smaller scales. It is only true for scales at the averaging scale and bigger than that. So this does not say the solar system has changed in size by a factor 2 in the past 1,000 million years. It says on the cosmological scale, everything scales with this scale factor. Okay, now, let me just briefly explain about the space sections. If you analyze that, what you will find is what it is saying is the following. It's saying take a typical point in the space t is constant and go out a distance d and look at a sphere here when you've reached a distance d. And if you're used to dealing with these metrics, you will be able to read off from that. Start off at a point r is 0 and then end up at a point r. The area of the two-sphere you get is 4 pi a squared of t f squared of r times is 4 pi a squared of t f squared of r. Choose in your space sections an arbitrary point. This is a space-time diagram. This is now a space diagram. So here I'm looking at 3 space directions, x, y, and z. Start off at the origin of coordinates, go out a distance d and draw a sphere at that distance. So that means you go the same distance d in all directions, it gives you a sphere. From this metric here, it follows that the size of that sphere depends on A, the scale factor at that time. It depends on F, this function here, evaluated at the time. And this is the unit sphere, which has area 4 pi, which is where this 4 pi comes from. So that's the area. Now, let's look at a fixed time and go to bigger and bigger radii, and you get the following 3 cases. If we plot that as a function of r squared, of the distance from the origin squared. In flat space, area is proportional to r squared, which is a straight line in this diagram. So that is the case k is 0. As you go out and out, distance scales as this area scales as the square of the distance. This is what we all expect and know from Euclidean geometry. But these space sections can be curved. If k is minus 1, in fact, what you get there, in the flat space here, you get a is proportional to r squared. In the negatively curved space, it's proportional to the hyperbolic sine squared of r. That means when you've gone out a certain distance in a negatively curved space, a sphere is bigger than it would have been in flat space. And as you go further and further, this gets worse and worse and worse. It's going to go up exponentially because in that hyperbolic sine there is an exponential. And so the size of spheres in a negatively curved space is much bigger than you might have thought. In a positively curved space, the area is proportional to sine squared. And that is less than r squared. Not only is it less than r squared, it reaches a maximum and then goes down to 0. So in a positively curved space, take bigger and bigger spheres, their area gets bigger, but then they come to a maximum, and they then start decreasing and come back down to 0. Wow, what is happening here? Okay, this is the same as the surface of a sphere. If you set out from the South Pole in a sphere and draw a circle, the circumference is 2 pi r in flat space, but it isn't 2 pi r on the sphere, it's 2 pi sine of r. And it reaches a maximum at the equator, and it then starts decreasing, and it goes to 0 once you hit the antipole. So this is a two-dimensional model. On the surface of a sphere, go out a distance r and look at the circumference of a circle. It gets bigger and bigger till it reaches a maximum at the equator, and it then starts decreasing till you get back to 0. And that's exactly the same that happens here. What you've got here is your origin, and here is the antipodes, the other side of the universe. Now what happens on the Earth? If you keep going through to the South Pole to the north, keep going, what happens is you arrive back where you started from. If you play around with these spheres for a bit, you will see the same thing happens. Keep going and you reach your antipodes. Keep going, it gets back to 0, and these 2 points must be the same. They are necessarily the same in a surface of constant curvature. So in a surface of constant curvature, it's like the surface of the Earth. On the surface of the Earth, set off in any direction, keep going, you reach your antipodes, keep going, and you arrive back from the opposite direction. If the universe is positively curved, if you set off in that direction and keep going, eventually you'll come back through that wall and end up back here. And that's the same if you go up or over there or any other direction. Surfaces of constant positive curvature are closed universes, and consequently they are finite. Now, these two ones here are what we call open universes, and they are infinite. Now, this is a huge, huge difference, which people don't emphasize enough. In the case k is plus 1, because the universe is closed, there's only a finite number of galaxies out there. It's a very big number. So how many galaxies have we seen so far? Do you know? 10 to the 11 galaxies, roughly, we've seen so far. Okay. Now, in a closed universe, there might be 1,000 times that, 1,000 times 10 to the 11, which is a huge number, but it's a finite number. In these cases, if we have the natural topology, then the number of galaxies is infinite. The amount of matter is infinite. I'm emphasizing this because I don't think people think enough about the implications of infinity. We tend to think of infinity, an infinite number of galaxies, we tend to think kind of it's a big number of galaxies. It's nothing of the sort. It's a bigger number of galaxies than any number you can conceive. Okay. Think of any number and it's bigger than that number. And I'll return to this in one of my later talks. There are serious problems with the idea that the universe is infinite. People talk about it glibly in the literature, but there are serious problems with the belief that the universe might be infinite. Now, I need to add in a statement here that k is 0 and k is minus 1 are infinite in the natural topology, in the topology you first thought of. Euclidean space, if k is 0, this is in fact Euclidean space. And Euclidean space has a natural topology in which if you keep going that way, you just keep going forever. That's Euclidean topology. But for k is 0 and k is equal to minus 1, it is possible the universe is closed, even, and that it will have a unusual, let's call it an unusual topology. So the statement is as follows. If k is plus 1, the universe is necessarily closed. If k is plus 1, there's no option. The universe must be closed. But if k is 0 or minus 1, I've described for you the geometry. It's given to you by this metric. But this is a local metric. There's no claim that this is the global metric necessarily. And globally, it could have a different connectivity. And a connectivity is what we can call an unnatural topology. E.g., a torus. Torus is the simplest example. If the universe was toroidal, there would be a distance d1 and a distance d2 and a distance d3. Let's say that would be